Today I will be presenting an important topic in this course, which is the second law of thermodynamics. You can find many prominent applications based on the second law of thermodynamics in almost every household. Some of the prominent applications would be a refrigerator, a car engine, and an AC conditioner. Before we start talking about the second law of thermodynamics, let me remind you quickly of what the first law states. In the first law of thermodynamics, it's only concerned about the conservation of energy, with no restriction on the direction of the process. The definition says that energy can neither be created or destroyed during a process. It can only change its form. Now, in order to understand this better, let's consider this cube of ice at a 0 degree Celsius, placed in a room with a temperature of 20 degrees. 5 minutes later, the cube of ice will melt into water. However, the total quantity of energy before and after the process are still the same, and the scale is still balanced. But in fact, the energy has changed its location or the form from one form to another. And this leads us to the fact that the total quantity of energy in the universe stays the same, but it can only transfer from one mean to another. However, the second law of thermodynamics came to correct the previous law and adds that energy always flows spontaneously from high to low, unless work is added to the system to reverse the process. There are two classical statements of the second law that places limitation for heat engines and refrigerators. The first one is Kelvin-Planck statement. It says that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce only a net amount of work, which means that energy can never change form without losing some of its quality. Let's consider this example. In order for a car engine to operate and produce work, there must be a high source of energy provided to the system, which in this case is the fuel in combustion chamber, denoted as Qn. However, based on Kelvin-Planck statement, you can never produce 100% of work from the provided energy, and there must be some energy lost during the process, denoted as Q out, that is exerted to a lower energy reservoir, which in this case is the atmosphere. Now, since it's impossible in real-life applications to operate a system with 100% efficiency, I can now introduce you a simple formula to calculate the coefficient of performance. In order to calculate the coefficient of performance, you need to divide the desired output you want to achieve over the required input of energy to the system. In this case, our desired output is the work net coming out of the system, divided by the required energy input, which is the fuel, denoted as Qn. Now moving on to Clausius' statement of the second law, which imposes that it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. Now, in the second example, it represents the system of a refrigerator. And in order to maintain a cold temperature in the fridge space, we need to transfer the heat from the refrigerator compartment to the outside atmosphere, which in this case a high temperature reservoir. And since we know that energy flows spontaneously by nature from high to low, we need to add work to the system to perform in the opposite direction, which follows Clausius' statement. Now, how can we determine the efficiency of this system? Simply use the COP formula, which is the desired output over the required input. In this case, our desired output is the cold refrigerated space, denoted as QL, divided by the required input to the system, which is work in. And that brings us to the end of my presentation. Thank you for listening.